Hello everyone, welcome to my channel Chemistry by ANR. Today's topic is bonding in coordination compounds. Now, what type of bonding exists in coordination compound? Before we start that, we have seen that Werner was the scientist who had described a part of the concept of bonding in coordination compounds, where he had told about the primary valency, the secondary valency, ligands getting connected, getting bonded to the central metal atom or ion. But his theory had certain limitations also. Werner's theory could not answer basic questions like why only certain elements they can form coordination compounds, why not other elements also. Now, why the bonds in coordination compound have directional property? Some of the bonds have directional properties. Why do they have directional properties? Why coordination compounds have magnetic and optical properties as well? So these are the questions which remained unanswered in Werner's theory. And later on, after Werner, many approaches have been put forward in order to explain the nature of bonding in coordination compounds, namely the valence bond theory, and that is which is known as VBT, the crystal field theory, which is CFT, ligand field theory, LFT, and molecular orbital theory, MOT. Now, in our syllabus right now, we are focusing on VBT and CFT. So, going on to valence bond theory, which is VBT, valence bond theory. Now, according to this theory, valence bond of what? Of the metal atom or ion, they get involved in bonding, but they lose their original form, and by the action of the ligand, or we can say by the approach of the ligand or the influence of the ligand, they use their orbitals, which are the valence shell orbitals. They are the n-1d nsnp. This is one set of orbital. Or they use the nsnp-nd orbitals. They use it for hybridization to yield a new set of equivalent orbitals having a definite geometry, and they are oriented in an octahedral manner, tetrahedral, square planar manner in order to form bonds with the ligand and the ligand orbitals. These hybrid orbitals, they overlap with the ligand orbital. So, just now we have said that the metal atom or ion, under the influence, under the approach of the ligand, they use their valence shell orbitals. That is what? They use their n-1d nsnp, or they use their nsnp and nd orbital for hybridization purpose, and as many orbitals are getting involved in hybridization, that many set of equivalent hybrid orbitals are getting formed, and they have a definite geometry. It can be octahedral, tetrahedral, or square planar. Now we have the same concept over here. For octahedral, the coordination number remains 6. For tetrahedral and square planar, the coordination number is equal to 4. But what will be the geometry? That depends on the hybridization state of the orbitals, or the hybrid orbitals that are actually overlapping with the ligand orbital. So the number of orbitals and types of hybridization is seen here. In coordination number 4, we have these two where we can have tetrahedral geometry or square planar depending on the state of hybridization. If it is sp3 hybrid orbital, then it is tetrahedral geometry. If it is dsp2, then it is square planar. So we have to see that the approach of the ligand or the influence of the ligand actually involves what type of hybridization states. Now, if the coordination number is equal to 5, then we have type of hybridization as sp3d, which is the trigonal bipyramidal geometry or the TBP geometry, the TBP structure. Now, if the coordination number is equal to 6, then we have octahedral geometry. But coordination number equal to 6 can have they can have different hybridization states as well. Like if I say coordination number equal to 6 can have sp3 d2 hybrid state, then it can be octahedral, or D2sp3, then also it is octahedral. But what is the difference between sp3d2 or D2sp3? If we see it is sp3d2, that means the nd orbital is getting involved in hybridization. And if it is D2sp3, then n-1d orbital is getting involved in hybridization. So, it is usually possible to predict what is the prediction of the geometry of the complex from the knowledge of its magnetic behavior on the basis of the valence bond theory. These types of questions you may see in NCERT, and similar questions you may get in your exam, be it your school exam or your board exam. There you will see that predict the geometry, predict the structure of the compound based on VBT, based on valence bond theory. So here we are seeing this type of complex, which is, this is a coordination entity, CONH3 whole 6, 3 plus. So NH3 whole 6, obviously coordination number is equal to 6, and we expect octahedral geometry. Now this octahedral geometry will be sp3d2 or d2sp3, that we have to see. And what will be the magnetic behavior? If it is having all paired electron, then it has to be diamagnetic, and if it has at least one unpaired electron, then it will be paramagnetic. So this is a diamagnetic octahedral complex. Why? You can see all the electrons are paired. None of the electrons are remaining unpaired. Now, what is happening over here is cobalt is having a 3 plus oxidation state, and in this 3 plus oxidation state it has 3d6 electronic configuration. So this is the ground state electronic configuration, which is 3d6. Now when the ligands are approaching, the 6 pairs of electrons, whichever we are seeing, 6 pairs of electrons, one from each NH3 molecule. Why? Because there are 6 NH3 whole 6. They occupy, see, 6 pairs of electrons, they occupy the 6 hybrid orbital. Now, where are these hybrid orbital? It has been seen that the electrons which are over here, they are getting paired up. So already we are having one pair here. Now these 2 electrons, they form another pair, and these 2 electrons, they form another pair. So by the approach of the ligand NH3, the electrons in 3d6 CO3 plus ground state gets paired up. And when it gets paired up, we are utilizing 3 of the degenerate orbital and the 2 orbital over here, along with 1s and 3p, they are undergoing hybridization, mixing, and they are forming D2sp3. Since it is 3d, so it is n minus 1d, 4s, so it is ns, and 4p, it is np. So we are getting 2d orbitals, 1s and 3p orbitals, giving rise to 6 set of degenerate D2sp3 hybrid orbitals. And in these 6 set of hybrid orbital degenerate having same energy, the 6 pairs of electrons from 6NH3 molecule gets involved. Why? Because nitrogen has a lone pair and coordination number 6 is involved. Thus, the complex has octahedral geometry because it is having coordination number 6, because it is having D2sp3 hybridization state by the action of the ligand, and because it is having all paired electrons, then it is actually diamagnetic in nature due to the absence of unpaired electron. All electrons are paired. In the formation of this complex, since the inner d orbital, that is n minus 1d orbital, is getting involved, it is known as inner orbital complex. Why? Because it is getting involved as I will say n minus 1d orbital is getting involved. It is a low spin complex or spin paired complex. Low spin complex actually means there is all paired electrons. There is all paired electrons and there is no unpaired electrons, so it is a low spin complex. So this particular compound or this particular coordination entity, we can see that it is first and foremost diamagnetic, having all paired electron. It is an inner orbital complex. Why it is inner orbital complex? It is the n minus 1d orbital is getting involved in hybridization, and it is ns and np that is getting involved. So the hybridization is D2sp3. And the third point is it is a low spin complex. Why? Because it is spin paired. Now another compound we can see over here, COF63-. The effect of the ligand over here is different. It doesn't cause the pairing of the 3d electrons in the ground state. Just see, this is your ground state, and here the 3d electrons are not getting paired up by the effect of the ligand. And so it is remaining unpaired over here, and the coordination number over here is again 6. The coordination number is equal to 6. So since the coordination number is equal to 6, we need 6 set of degenerate orbital, that too hybrid orbital. By the approach of the ligand, the orbitals like 4s, the 3,4p and 2,4d, they undergo intermixing, and due to the approach of the ligand, due to the repulsive interactions, and due to the difference in the energies of the orbitals that arise on ligand approach, we have sp3d2, sp3d2 hybrid orbital state. So this is point to remember is say it is ns, it is np, and it is nd orbitals that are getting involved, 4s, 4p, 4d. And since the 4d orbital is getting involved, it is outer orbital complex. So it is no more inner orbital complex. It is not involvement of n minus 1d. No 3d. It is 4d. So it is outer orbital complex. And see over here, we have unpaired electrons. And so they are high spin or spin free complex. And if there is unpaired electron, it shows paramagnetic behavior. So you may be told to explain the fact using VBT why CONH3 whole 6 3 plus is an inner orbital complex, is a low spin complex, is diamagnetic, whereas COF6 3 minus is outer orbital complex, high spin and paramagnetic. This is how you are going to explain. So what is the step? Let us see once. Let us just try to recall what we have seen. Like CONH3. Just a minute. So, like over here, CONH3 whole 6 and it is 3 plus. Suppose this is being given to us, 3 plus. Now we will see what is the oxidation state. Now NH3 is neutral ligand. So this will be CO3 plus. If it is CO3 plus, it has 3d6 ground state electronic configuration. So you just have to form this 3d like this over here. So it is 1, 2, 3, 4 and 5 and 6. And so this is your 3d6 configuration. After 3d comes your 4s. After 4s comes your 4p. It's like this. The ground state configuration is like this. Due to the approach of the ligand, which is NH3, later on we will come to know that NH3 is a ligand. Under CFT we'll see that it is having such a field effect that it can cause pairing of the electrons in the metal orbital, for which actually here the electrons get paired up. So how to write? We will just write excited state and then we will pair up the electrons. So how to pair up again? So to pair up the electrons, one pair already present, these two will form another pair and these two will form another pair. So we are actually left with, so this is 3D, this was 3D, this is 4S and this is 4p. So now we will utilize D2sp3. So we can utilize D2sp3. After writing D2sp3, you can immediately write it is inner orbital complex. So you declared it is inner orbital complex. You can show it is all paired electrons. You need not write too many lines. The way you are writing, the way you are expressing your answer can be short, can be detailed manner if you write it in this way. So all paired electron, obviously it is diamagnetic. And involvement of inner d orbital, so it is inner orbital complex. Since it is all paired, so it is a low spin complex as well. So you told the three important points: inner orbital, diamagnetic, low spin. These are what asked in your exam to clarify. Next, moving on to a coordination number equal to 4, that is tetrahedral complex. In a tetrahedral complex, either we can, in a coordination number 4, either we can have sp3 hybridization state or dsp2. So if it is tetrahedral complex, we all know it has to be sp3 hybrid state. So this is one example that is given, NiCl4 2 minus. Now in this, nickel has oxidation state is what? X minus 4 equal to minus 2. So X is equal to plus 2. So Ni2 plus, in its ground state, it is having this type of electronic configuration. And what is that? It is 3D8 configuration. So in this 3D8 configuration, by the action of Cl minus, what happens is the electrons you see, they are not getting paired up. It is not having such a very strong field effect to cause a pairing of electron. But we need 4 hybrid orbital for a coordination number equal to 4 to accommodate the electron pairs of Cl minus. So each Cl minus will give one electron pair. For a coordination number 4, we need 4 such orbitals, and that is 1s and 3p forming sp3 hybrid orbital. So here we can see in this complex, nickel is having a +2 oxidation state, 3d8 configuration, and the hybridization is what? It is sp3 hybridization. And all electrons are paired up. There is no, I will say, unpaired electron over here. No, here we are getting to see 2 unpaired electron. So you just mark over here that this is unpaired electron. So we expect paramagnetic behavior, and now you mark it over here, it's paramagnetic. Why? Because it has unpaired electron, contains 2 unpaired electron. See, if it contains even 1 unpaired electron, then also it will be paramagnetic in nature. So this was one of the compound or one of the complex. Going to the next, this one, nickel tetracarbonyl, having 0 oxidation state of nickel. So this is again, it has a tetrahedral geometry, but it's diamagnetic, you know. So why? Because nickel is having a 0 oxidation state. It does not contain any unpaired electron. So it is diamagnetic without any unpaired electron. Now coordination number equal to 4 can also have dsp2 hybridization state, that is a square planar geometry, dsp2 hybrid state. So the example over here is this, it is tetracyanidо nickelate and nickelate 2. So nickel is having +2 oxidation state, electronic configuration 3d8, Cn minus is quite a strong ligand, and so it has the capacity to pair up these 2 electrons and give you dsp2 hybrid state, where the 4 electron pairs of Cn minus can be accommodated. And are we seeing any unpaired electron? No. So it is having 0 unpaired electron and is diamagnetic. So this is how we are going to explain with the help of VBT. Now, it is important to note that the hybrid orbital do not actually exist. In fact, hybridization is a mathematical manipulation of wave equation for atomic orbitals involved. Just like we were explaining, under the action of so and so ligand, the electrons are getting paired up, and so the orbitals, the rest of the orbitals, depending on the coordination number, gets hybridized. Isn't it an assumption? So it is a hybridization is actually a manipulation of the wave equation. But as of now, you have no way. If you have to explain in terms of VBT, you have to go in this method. Now the magnetic properties, we have seen that magnetic properties can be explained. Now magnetic moment, if it has magnetic property, it also has a magnetic moment, and we can calculate the magnetic moment in a mathematical manner, and then we can find out from the number of unpaired electrons. Okay, so the results can be used from the number of unpaired electron, and so the structures that are adopted can be explained by this method. So wherever we have actually seen how to find out the oxidation state of the central metal. We have seen how to write the ligand effect. We have seen how to judge whether it is paramagnetic or it is diamagnetic, depending on how whether there is any unpaired electron or there is 0 unpaired electron. So if we have to actually find out the geometry of a complex, then what can we do? How can we find the geometry of a compound? Say the spin only magnetic moment is this, predict the geometry. So what we can do? Here we can see it is Mn2 plus ion. And here we can see it is having a coordination number of 4. And it will be, if it is coordination number 4, it will be either say tetrahedral or it can be square planar. Now, if the magnetic moment is this, it should be tetrahedral in shape rather than square planar. How do we know? Because of the presence of 5 unpaired electrons. Again, you may say, how do we know that? We have to work out on the ground state configuration, and Br minus is not a strong ligand, it's a weak ligand. So it's a weak field ligand. So here it's a weak field ligand. Br minus. So there will not be any pairing. Now we have to see how many unpaired electrons are there. If N is my unpaired electron and I need to mathematically find out the magnetic moment, I can say the magnetic moment is B, this is mu B, which is the magnetic moment. It can be given as root over of N into N plus 2 Bohr magneton. This is the unit. Okay, so where N is number of unpaired electron. So straight away what we can do is we can find how many unpaired electron exist over here. We can place over here and then we can justify as well. But that much is not required. We can explain it by logical reasoning that we are seeing here. Now, what are the limitations of VBT? VBT cannot give you so many things clearly. It gives too many assumptions. And what is it? It actually does not give the quantitative interpretation of magnetic data. This is not the one which I told you. This is not as per VBT. Nowhere over here you will see VBT is giving you this formula. Since we know magnetic moment, now we know after so many things coming up, after CFT coming, after LFT coming, after the concept of magnetic moment coming, we know it is root over of N into N plus 2 Bohr magneton. But nowhere in VBT you can see that it is given that it is root over of N into N plus 2. So there is assumption with the structure we are assuming. Like here we have said, isn't it an assumption that it should be tetrahedral in shape rather than square planar because of the presence of 5 unpaired electron? So we will see where the number of unpaired electron is greater, where it is less, and accordingly we are saying, so that is an assumption. It does not explain the color. So the color concept is not here. It does not give any quantitative interpretation, the value of the thermodynamic or the kinetic stability of the coordination compounds, or rather the relative stability of the coordination compound. Which of the coordination compound will be more stable and why? Now, it does not make exact predictions regarding tetrahedral and square planar structures with 4 coordinate complexes. Why with a coordination number 4 we can get a tetrahedral as well as square planar? That we have assumed that the ligand is having this field effect, this is having that field effect, but that is not the outcome of valence bond theory. It is only this much known from valence bond theory that under the action of Br minus the electrons are not getting paired up. Under the action of Cn minus the electrons are getting paired up. But why? There is no categorization of a weak field or strong field ligand, which is actually the cause why it is getting paired up in presence of a strong field ligand and why it is not getting paired up in presence of a weak field ligand. So these shortcomings of the VBT is overcome in the next thing, which is crystal field theory. So we are going to meet in the next module, which is crystal field theory, CFT. Till then, bye all of you.